Today, we're going to be evaluating this problem and obtaining the shear and bending moment diagram equations and plots. To start, we always get the support reactions. In this case, we're going to get the tension from the cable and the support reactions from the pins. The support reaction at AY is 99 kip. I wrote something that looks like a 4, but it is 99 kip. For the shear and bending moment diagrams, we do not need the AX reaction, but we can calculate it nonetheless if we wanted to see it on our loading diagram. We can now start with our draw loading diagram, which is very similar to our free body diagram, except all the unknowns are now replaced by the known loadings. Again, this is supposed to be 99 kip. I don't know why I kept writing it like a 94, but it is 99 kip. Don't forget that you want to take into account the vertical component of the tension, because that's a component that's going to show up on your shear diagram. We write the axis for the shear and bending moments, plots, and we start to evaluate each section for shear and bending moments. Remember that you cut between discontinuities like I'm doing here. And that gives us the section that we're going to analyze, like section A and B. Now we draw the free body diagram of section A and B. Remember that you do not reach B with this cut. Now I am writing the X component of the support, but that is not going to have an effect on our shear or our bending moments, diagrams or functions. And we can calculate what those are. We come here to the plot and we pay attention to the initial discontinuity of 99 kip, and we go up accordingly. Then we use the shear function and we go from A to B using that value. We do the same thing with the bending moment. Since there's no couple at A, there's no jump at A. And we plot as a function of X. Now we're ready for section BC. We do the same process all over again. Draw the free body diagram. Remember, you don't reach C, so it never reaches 100 kip per foot, up from the 400 kip foot that we have before. For the distributed load here, we do have a function WBC of X. We need to determine what that function is if we wanted to integrate it to obtain the shear. Because it's a linear equation, it's simply mx plus b. And using our loading diagram, we can calculate the slope. And with the known value of the loading at B, which is 1 foot, we can calculate the y-intercept of our equation. And now we have the equation of our distributed load, WBC of X. Since it is related to our shear diagram, we go ahead and substitute the value in. So our minus 200x plus 600 W distributed load becomes 100x squared minus 600x plus a constant that needs to be evaluated. We evaluate it from the shear plot because we know the value of the shear at 1 foot. And that gives us the constant of integration, and we have now that our shear is 100x squared minus 600x plus 599 kip. We can now plot that section and obtain the value where it ends at 2.5 feet based on our function shear BC at x. We integrate it to obtain our bending moment function, and just like before, we need to evaluate the constant of integration, and we know the value of the bending moment at 1 foot. And with the constant of integration, we have the full function for the bending moment in that section. We substitute the values of x in it, and we realize that the point where my shear diagram crosses the axis is the maximum value of my function for the bending moment, and we land at minus 90. We go back and check for discontinuities, in this case the vertical component of the tension, creating a jump that takes us to 0 on the shear. We also notice since there is no more point loads or vertical distributed loads, the shear will remain at 0 because there are no vertical loads that could shift it. We can demonstrate that too by doing the same cuts through the other discontinuities. So if we evaluate section CD the same way that we did the previous versions with our free body diagram, and we sum our forces in Y, we'll see that the shear between C and D will be 0. If we sum the moments for the bending moment in section CD, we get a constant, which continues from minus 90 to the next discontinuity. Now at this location there is a couple, so it's going to cause a jump of 100 foot in the opposite direction of the external couple. Again, our shear remains 0, so our slope in the bending moment diagram should also remain 0. Up to the next discontinuity. And at that point, we find the last discontinuity, which is the couple of 10 kip foot. We can demonstrate this again on section DE by drawing the free body diagram and obtaining the internal shear and bending moment functions. And now we have the complete set of functions for the beam and the plot of the shear and bending moment diagram.